If one day every compass on Earth suddenly pointed the wrong way, not because the needle failed, but because the planet itself changed polarity, what would fall apart first? Our maps, our power grids, or our quiet faith that some things in this world are truly unshakable? Tonight, we're going to follow that question straight down into the machinery of reality. We'll begin beneath our feet, inside Earth's core, where molten metal circulates like a living engine and generates an invisible magnetic shield that has protected life for ages. Then we'll leave Earth behind and cross to Jupiter, where NASA's Juno mission forced scientists to confront a core that isn't solid at all, something diffuse, fuzzy, and far more unsettling than a simple boundary between center and surface. From there, we'll plunge into the Sun itself, tracing a single photon born in nuclear fusion as it fights its way outward, colliding, scattering, and wandering for hundreds of thousands of years before it finally escapes to become the morning light on your face. And just when you think you've reached the deepest center possible, the story turns outward toward the Milky Way's hidden heart and the ancient stars sleeping there before landing on a truth that feels almost personal. The universe may not have a center in the way our minds crave. Stay with me to the end, and you won't just learn how these phenomena work, you'll see why stability is often born from chaos, and why we keep searching for a center to hold onto. The mind leans on certain things as if they were nails in the wall of reality, small fixed points that let everything else move without becoming unbearable. One of those quiet nails is the idea that there is a direction called north, and that it is simply there, waiting for you whenever you need it. Maybe you first met north as a child, standing over a map, with a thin arrow printed at the top, always pointing the same way. Or maybe you met it through a phone screen, a red needle turning in a circle until it settled into certainty. Hikers trust it. Pilots trust it. Satellites and submarines trust it. You grow up into a world where north is one of the few directions that seems to belong more to the planet than to you. But the north that your compass knows is not the north that your geography teacher showed you. The point at the top of the map, where Earth's axis pokes through the crust, is the geographic North Pole. It is defined by rotation. It is an imaginary pin pushed through the planet at the places where the spin narrows to a point. That place does not slide around very much on human timescales. It is not what your compass follows. Your compass listens to a different north, a wandering one. A north that exists only because deep inside the planet, liquid metal is moving in patterns that never quite repeat. The magnetic North Pole, the one that pulls the needle, is not a single clean point. It is a region where the lines of the magnetic field dive inward. That region moves. It drifts across the surface of the planet like a slow animal you can only see from far away. Through equations and instruments, over the course of the last century or so, that animal has crossed thousands of kilometers, leaving the Canadian Arctic and marching toward Siberia. Its speed has changed over time, at some points covering dozens of kilometers in a single year. The map in your school book did not show that motion. It rarely does. Stability is easier to print. Most of the time, you do not notice this drift. Navigation systems quietly adjust. Airports repaint their runway numbers when the magnetic reference changes too much. Your phone downloads updated models of the field without telling you. The world of coordinates flexes around a moving reference, and daily life continues. But underneath this calm, something more unsettling is true. The direction a compass points is not guaranteed. It is not a fundamental property of space. It is an emergent side effect of a restless, churning interior. And that interior has a habit, played out many times across the deep past, of doing something that feels almost unthinkable from the surface. It reverses. There have been many full flips of Earth's magnetic field over geological time. Not a handful. Many. On average, they are separated by hundreds of thousands of years. But they do not obey a tidy schedule. Sometimes, the planet holds the same magnetic orientation for tens of millions of years. Sometimes it changes more often. The record written into rock layers shows a long barcode of normal and reversed periods. To the planet, swapping north and south is not a once-in-a-lifetime catastrophe. It is part of its ongoing behavior. To a human mind that likes fixed points, that fact lands strangely. It is one thing to learn that mountains rise and erode, that continents drift, that climates shift. Those changes are large, but they feel slow enough to sit outside a single human story. The idea that something as basic as the direction of north can change entirely is a quieter kind of shock. It does not tear cities down in an instant. It pulls gently at the trust you place in the idea of permanence. When people imagine a magnetic reversal, they often picture a sudden snap. One moment, all compasses point roughly toward the Arctic. The next, they swing and lock toward Antarctica. A cosmic switch is flipped. A clean before and after. Nature rarely works in that kind of neat jump. Between one stable orientation and another lies a long interval of confusion. The field does not simply weaken a little and then politely reassemble in the opposite direction. It distorts. It sprouts extra poles. Patterns that were once simple begin to knot. During these transitions, the strength of the global field can drop to a fraction of its usual value, enough that the protective bubble of magnetism around Earth thins, enough that more charged particles from the Sun and from distant space can reach the upper atmosphere, enough that the sky at night, at lower latitudes, might glow with auroras that once belonged only to polar regions. None of this happens on the timescale of a news cycle. The changes unfold over thousands of years, perhaps tens of thousands. They would not be events in the human sense of the word. They would be background conditions, slowly changing the canvas on which all events take place. Yet that slowness does not make them harmless. A weaker magnetic field means satellites encounter more radiation on each pass through space. Electronics fail more often. Communications become less reliable. Navigation systems that depend on a stable field grow noisy. You can rewrite software. You can build better shielding. But every adaptation is a negotiation with a planet that is not obliged to meet you halfway. Life on the surface is less fragile than circuitry. Organisms have endured past reversals. There is no clear pattern linking flips of the field with the great mass extinctions. The biosphere bends. It absorbs the extra stress, shifts slowly, finds new balances. In that sense, the living world has already passed this test many times. Civilization has not. In a world where trade routes, power grids, financial systems, flight paths, and global positioning networks are all threaded through orbiting hardware and invisible signals, the question of what fails first gains a different weight. Imagine a field that has weakened for so long that satellite insurance companies quietly rewrite their models. Launch providers adjust orbits to spend less time over radiation hotspots. Astronauts learn to respect new forbidden regions, slices of space around Earth that are no longer safe in the way they once seemed. None of these shifts would announce themselves as a single disaster. They would accumulate as a new kind of normal. Now, stretch that picture further. If the field kept changing, if temporary poles appeared and disappeared in strange locations, if the once smooth dipole fractured into a more chaotic pattern, every system that assumes a simple, planet-wide magnetic geometry would become, slowly, unreliable. Not useless, but noisy, patchy. Trust would drain from compasses and maps and models in the same way it drains from an institution that keeps rewriting its rules. Underneath the technical concerns, another question waits, quieter and more personal. When a framework you never questioned begins to move, What exactly are you losing? It is not just a direction on a dial. It is a sense that some scaffolding of the world stands outside of history. That there are a few reference lines you can lean against while everything human changes. You can ignore those lines most days. You do not wake up thinking about the magnetic field. But some part of you behaves as if such things are secure by default. A drifting North Pole. A field that sometimes fades and rebuilds itself with the opposite orientation. Suggests something else. It suggests that even the background is a participant. That there is no pure stage on which life and thought play out. The stage itself creaks and shifts and occasionally turns upside down. For a species that arrived very late in cosmic time, building meaning on top of assumptions about stability, that realization is not dramatic, it is subtle. Like noticing that a trusted building has always had a slow, constant sway, and that your balance has depended on it without your consent. If you want to understand what it would mean to live through such a long, invisible transition, you have to follow the question downward. You have to look past the maps and the satellites, past the instruments and the stories, into the place where the field is born, into the moving metal that turns the whole planet into a kind of generator. Powerful and fragile at the same time. To understand that generator, you have to peel the planet back in your mind, layer by layer, until the ground that feels so definite under your feet turns out to be just a thin shell over something that never rests. Start with what you can picture. A globe, perhaps, the kind that sat in a classroom or on a shelf. The blue and green surface, the continents and oceans, seem like the defining features. We live there. Our cities, our borders, our stories cling to that film of rock and water. But if you could slice the planet open and spread its interior out in front of you, that surface would shrink to a fragile skin. Beneath it lies a thick, dense mantle of hot rock that flows, very slowly, over very long spans of time. Deeper still, you would reach the core, a region dominated by iron and nickel. The outer part of that core is liquid. The inner part is solid, pressed and frozen by pressure so extreme that not even intense heat can fully melt it. That simple description, solid inside, liquid outside, already sets up something important. The liquid outer core can move, it can circulate, it can convect, with hotter, lighter fluid rising and cooler, heavier fluid sinking. These motions are not gentle, they are turbulent, swirling, constantly shifting. You might think of boiling water, except stretched over thousands of kilometers and slowed down so that one cycle can take years. Where there is moving metal, there can be electricity. In the outer core, iron is not just a heavy element, it is a conductor. As this conducting fluid moves through any existing magnetic field, it generates electric currents. Those currents, in turn, create more magnetic field. The process loops on itself. This is the essence of a dynamo, mechanical motion feeding electromagnetic structure. The idea that Earth has a self-sustaining dynamo at its heart is not just a metaphor. It is the best explanation scientists have for why there is a magnetic field at all. The field is not a leftover imprint from some ancient alignment. It is actively maintained, moment by moment, by the restless movement of molten metal deep below your feet. Not every planet has managed this trick. Mars shows signs that it once had a global magnetic field. Long ago, today, only faint, patchy remnants remain locked into certain rocks, without a strong, active field. Its atmosphere has been more exposed to the solar wind, a stream of charged particles from the sun. Over immense time, that wind has stripped away much of the Martian air. The planet still has weather, still has dust storms, still has ice, but its shield is mostly gone. Venus, similar in size to Earth and wrapped in an even thicker atmosphere. lacks a strong internal dynamo as well. Its slow rotation and different internal conditions do not favor the same kind of magnetic machinery. Whatever is happening at its core, it is not producing the kind of orderly, planet-spanning field that turns a compass needle. Gas giants like Jupiter and Saturn do have strong magnetic fields, but they arise from different materials and pressures, from layers of metallic hydrogen rather than molten iron. Their dynamos operate under conditions that are hard even to imagine. Against that backdrop, Earth's field looks less like a default setting and more like a specific, fragile achievement. The combination of a partially molten, metallic outer core, enough internal heat to drive convection, and a rotation fast enough to organize the chaos, is not guaranteed. It is contingent. It depends on how the planet formed, what it is made of, how it cools. Life has grown up under the protection of this invisible structure. For more than 3 billion years, organisms have evolved, diversified, and endured while a magnetic bubble around the planet has deflected much of the charged particle flux from space. The field does not make Earth safe in any absolute sense. It simply tilts the odds in favor of more stable atmospheres, less radiation at the surface, more time for complexity to accumulate. From the surface, none of this is obvious. You do not feel the core. You do not hear it. You do not wake in the night aware that far below, liquid iron is flowing in great loops, generating currents and fields and shielding that you will never touch. Your senses are tuned to other scales. That mismatch is part of the unease here. The most basic supports under our world are both immense and inaccessible. You cannot walk to the core. No drill will ever reach it. Every statement about it is an inference, drawn from the way seismic waves curve through the planet, from the way gravity behaves, from the patterns observed in the surface field and in the rocks that preserve its past. We are, in a very literal sense, living on top of a machine that we can never visit. When you hear the word machine, you might think of regularity, of neatly spinning parts and predictable output. The dynamo in Earth's outer core does not fit that comfortable image. It is a machine made of turbulence. Currents twist and fold. Vortices merge and break apart. Heat leaks out unevenly into the overlying mantle, guiding the flow in complicated ways. In such a fluid, every parcel of metal is responding to multiple influences at once: buoyancy, Coriolis forces from the planet's rotation, friction, magnetic feedback. If you could see it in cross-section, it would look less like gears and more like weather. And yet, from this mess, a large-scale structure emerges, a magnetic field that, at the surface, looks approximately like the field of a giant bar magnet, with one north and one south, lines of force arching from one hemisphere to the other. The details are more complex, but the overall picture is simple enough that a child can draw it with a few loops of a pencil. That contrast is worth lingering on. Deep chaos, surface order, countless possible flows in the liquid core, one actual dipole field that manages to dominate. What selects it? Why is there not a tangle of unrelated small fields instead of one that spans the globe? Part of the answer lies in how magnetic fields interact with conducting fluids. When a strong, large-scale field forms, it can influence the flow that created it, suppressing some smaller eddies and favoring motions that reinforce the existing structure. The system becomes self-organizing. Once a particular pattern grows large enough, it tends to persist. But persist does not mean last forever. Over very long times, the flow in the core can reorganize. Heat patterns in the mantle can change. The overall energy driving convection can wax and wane. The field responds. Sometimes it weakens without flipping. Sometimes it decays and rebuilds with the opposite polarity. The dynamo is not a static blueprint. It is a process. When you think of a generator in a power plant, You can picture engineers and maintenance schedules and design choices. You can imagine reasons. You can point to the people responsible for keeping the lights on. With a planetary dynamo, there is no one in charge. The only law is that systems far from equilibrium, given enough time and enough degrees of freedom, explore their own possibilities. Living on such a planet means that many of the conditions you rely on are not promises. They are accidents with long lifespans. From a certain angle, that realization is quietly destabilizing. The steady magnetic field you inherit at birth, the field that guides animal migrations and protects circuits and shapes, the auroras, is just the current phase of a deep, convective experiment. It is not owed to you. It is not tailored for your civilization. It happened to be here when your species arrived. And yet, you build as if it were permanent. How else could you build? This is one of the strange tensions of being a thinking creature on a geologically active world. You need stability to plan, to invest, to raise children, to write books and launch spacecraft. But the stability you lean on is often temporary when measured against the timescales of the systems that create it. The core does not know about your need for reassurance. It does not know about need at all. It moves according to temperature gradients, rotation, composition, and the physics of magnetized fluids. It responds to the slow cooling of the planet, to the growth of the solid inner core, to variations in how heat escapes through the mantle above. Over millions of years, those influences add up. They tilt the dynamo toward new configurations. If you imagine the history of Earth's magnetic field laid out as a long line, with normal and reversed intervals alternating, like stripes, you can see the dynamo's restlessness in one glance. Wide bands, where the field held the same orientation for tens of millions of years. Narrow bands where it flipped more frequently. No obvious period. No metronome. On that long line, your entire life would occupy less than the thickness of a human hair. Your civilization, from its first cities to its present satellites, would be a smudge. From the perspective of the core, the question of whether the field stayed mostly steady during that brief smudge, or shifted, or weakened, is a small detail in a much larger story. But from your perspective, that detail is everything. If the dynamo is stable on human timescales, the field looks reliable. Compasses work. Satellites can be designed with certain expectations. Radiation exposure in low orbit can be mapped and managed. Space agencies write manuals that assume a certain background. If the dynamo enters a more chaotic phase, the maps change. What once felt like a background constant becomes a moving parameter. You discover, perhaps slowly, that the planet you live on is not just a stage, but an active participant in the drama. There is a particular kind of humility that comes from this realization. Not the kind that says humans are insignificant because the universe is large, but the kind that notices how much of what we call normal rests on processes that never consulted us. You can learn the equations of magnetohydrodynamics, trace the feedback loops of field and flow, simulate reversals on supercomputers. You can gain real understanding, but you cannot negotiate with the outcome. The dynamo does not care if an upcoming oscillation is inconvenient for satellite design or for the way you draw maps. All you can do is observe, model, adapt, and accept that the magnetic heart of the planet will keep beating in its own way, on its own schedule. To see why the field that rises from that heart has the shape it does, why it prefers two main poles instead of a random scattering of magnetic islands, you have to look at how rotation twists those convecting flows, turning straight motions into spirals, and spirals into a global pattern. Rotation is not just a background habit of the planet, it is a rule that every moving thing inside must obey, even if it would rather travel in a straight line. If you stand on the surface and watch clouds curl around in a storm, you are already seeing what happens when motion and rotation meet. Air tries to flow from high pressure to low pressure. The spinning Earth bends that motion sideways. In the northern hemisphere, large weather systems swirl one way. In the southern hemisphere, they swirl the other. The same physics that draws spirals in the sky is at work, invisibly, far below, in the dark metal of the core. This bending has a name, the Coriolis effect. It is not a force in the way gravity is a force. It is a consequence of looking at motion from a rotating frame. If you could stop the planet and watch the same flows from outside, they would be simpler, but you are not outside. You live on the spinning object. Everything you measure is filtered through that spin. Deep in the outer core, molten iron rises where it is slightly hotter and less dense, and sinks where it is cooler and heavier. Left alone, those currents might move in broad, looping paths. Instead, rotation twists them. Any upward motion is nudged sideways. Any horizontal motion curves. Over time, this constant sideways push turns straight, rising columns into helical paths, like springs wound roughly around the axis of the planet. Imagine tall, invisible spirals of liquid metal, aligned roughly parallel to the rotation axis, rising and falling in slow, powerful cycles. Each spiral carries electric charge because the fluid is conducting. Moving charge creates magnetic fields. In each of those columns, circular magnetic loops form around the rising and sinking flows, wrapping the motion in linked lines of force on their own. Those loops might point in many directions, cancelling one another out, but the overarching symmetry of rotation gives them a preferred orientation. The columns tend to align, their individual fields combine. What you get, when you sum over the whole outer core, is not a chaos of tiny, confused magnets, but a large-scale pattern. Field lines leave one hemisphere, arch through space, and dive back into the other. A dipole. From the surface, this dipole looks simple enough to draw on a page. A north pole, a south pole, lines arcing from one to the other. It feels like a basic feature of the planet, as straightforward as the line between day and night. But simplicity here is deceptive. It is not the simplicity of a basic rule. It is the simplicity of an average taken over enormous complexity. There is a quiet lesson in that. Many of the things that feel stable in your life are not the result of fundamental stillness. They are the result of countless moving parts, constrained just enough to make a pattern that lasts longer than you do. A relationship that holds over decades. A language that remains intelligible across centuries. A city that stands through many generations. From inside, each of these can feel necessary, almost inevitable. From outside, given enough time, each is revealed as one temporary arrangement among many. Inside the core, the Coriolis effect is relentless. It does not switch off. With every rotation of the planet, it keeps nudging flows into columnar structures, keeps encouraging spirals. If the rotation slowed dramatically, the geometry of those flows would change. The dynamo might weaken or reorganize. The fact that Earth spins once each day is not just a rhythm for sunrise and sunset. It is a parameter in the engine that keeps the field alive. You can think of rotation as a kind of sculptor. It does not create the raw material. The iron is already there. The heat is already there. The gravitational pull is already there. But by insisting on a particular frame of motion, it carves certain shapes out of the chaos. Spirals instead of straight lines. Columns instead of blobs. A global dipole instead of a soup of local fields. From the point of view of the molten iron, there is no stability here. Every parcel of fluid is constantly being turned, stretched, compressed, heated, cooled. The flows that look steady in a simplified diagram are in reality full of eddies, fluctuations, and sudden reorganizations. Yet when you step back and look at the field from outside, averaged over years, you see something that resembles a steady bar magnet. This is the illusion of stability. The field is not truly still. It only looks still because you are smoothing it over in space and time. You are not watching every twitch of the core. You are watching the long, course outcome. The same trick happens in the sky. When you look up at the constellations, it is easy to feel as if they are fixed pictures. Lines connecting stars, month after month, year after year. In reality, each star is moving in its own orbit, pulled by the combined gravity of the galaxy. The patterns you learned as a child are temporary arrangements of objects that share only a passing alignment from your particular vantage point. They will slowly deform over tens of thousands of years. But compared to a single human life, they are stable enough to feel eternal. In your own mind, there is a similar averaging. You might describe yourself with a handful of traits, a personality, a sense of who you are. That sense feels continuous, but underneath it is a stream of changing moods, shifting preferences, memories that fade and are replaced. The story you tell about yourself is like the dipole field, a simple, coherent shape drawn over a far more intricate, restless interior. It is not that the shape is false. It is just that it is not the whole picture. Back in the core, the Coriolis effect does more than create spirals. It also limits how the flows can reorganize. The rotation axis becomes a kind of reference line. Large-scale motions tend to respect that line, forming structures that are elongated along it. These are sometimes described as columns wrapping the core, extending from near one pole to near the other. Where those columns intersect the outer boundary of the core, they imprint their magnetic signature on the field that reaches the surface. That imprint is not perfectly symmetrical. Earth's field has patches where it is stronger or weaker, regions where the direction deviates from the clean dipole picture. Over decades, those patches drift, new anomalies form, old ones fade. The North Magnetic Pole itself is wandering faster now than it was a century or two ago. The pattern is not fixed. It is a moving compromise between opposing tendencies in the flow. Still, when you step back far enough, the dipole remains the dominant note. As long as the dynamo is not in the middle of a reversal or a major reorganization, the field keeps roughly the same broad orientation. Compasses point roughly the same way. Animals that navigate by magnetism can still rely on a global gradient. The chaos inside and the order outside coexist. You could say that much of what we call stability is of this kind, an emergent alignment that holds not because any part of the system is still, but because the movements are constrained into a band of possibilities. A marriage stays together, not because the people in it do not change, but because they keep negotiating the changes. A culture keeps a recognizable identity, not because its members think the same thoughts as their ancestors, but because there are enough shared practices to tie the differences together. On geological timescales, even this kind of constrained stability is provisional. The spirals in the core can reorganize in such a way that the field weakens, eventually reverses. When that happens, the illusion of a simple, reliable dipole breaks down. Additional poles can appear. Regions of reversed field can coexist with regions of original orientation. The map of the field becomes complicated in a way that no classroom diagram ever suggests. From the surface, if you could see that evolving pattern in real time, it might look like a slow, global weather system of magnetism, storms and clearings unfolding over millennia. From one lifetime to the next, it would appear almost unchanged. From the perspective of the core, it would be just another episode in a long sequence of reorganizations. There is a quiet discomfort in realizing how dependent we are on such episodes being well-behaved across our own narrow window of time. We design technology that assumes a certain range of field strengths, and orientations. We write navigational standards and safety protocols based on measurements made over a few human generations. Implicit in all of that is a belief that the field will not do anything too surprising, too quickly. The Coriolis effect, twisting flows into spirals, has so far helped enforce that belief. By funneling motion into organized structures, it favors large-scale fields that change slowly compared to human lives. But nothing in the physics guarantees that this will always feel as calm from our vantage point as it has so far. At some future point, deep within the outer core, patterns of flow will shift in ways that let the dipole weaken more dramatically. Regions of reversed polarity will grow. The once simple illusion of a single, steady north and south will blur. Maps will have to be redrawn more often. Space agencies will have to revise their models more frequently. Migratory animals may face new gradients to interpret. In that era, whoever is alive will have to adjust their sense of what counts as reliable. The old background assumption that the field is a quiet constant will no longer hold. A piece of the world that felt like an anchor will reveal itself as another moving part. The planet, for its part, will simply continue. The Coriolis effect will keep twisting flows. The core will keep convecting. The dynamo will keep exploring its space of possibilities. And the field that rises from all of this motion will keep writing its history into rocks, leaving records for any patient intelligence, much later, to read and wonder how many illusions of stability it built while the ground beneath its feet was quietly spinning, churning, and changing all along. The core keeps changing, but it does not keep a diary. For that, the planet uses stone. Imagine molten rock rising along a mid-ocean ridge, deep under a cold, dark sea. It erupts, spreads, and begins to cool. While it is still liquid, iron-bearing minerals within it behave like tiny compasses, free to swivel under the influence of Earth's magnetic field. As the lava cools below a certain critical temperature, those minerals lock in place. Their microscopic needles freeze, each one pointing along the direction of the field at that moment. Once that happens, the rock forgets that it was ever fluid. It behaves like solid basalt. Waves crash above it. Sediment settles on top. Creatures evolve, live, and disappear without ever seeing it. But inside, the alignment of those tiny magnetic needles remains, quietly preserving a snapshot of the invisible structure that wrapped the planet when the rock hardened. If you could hold a piece of that basalt in your hand and see the orientations of all those grains at once, you would be holding a record of a magnetic now from some lost time. Not a story told in language, but in vectors. When geophysicists began measuring the magnetization of rocks on the seafloor, they expected some noise, some local variation. What they found instead was a pattern. Bands of rock on one side of a mid-ocean ridge had magnetizations pointing in one direction. Bands of similar width on the other side had magnetizations pointing the same way, farther out, parallel to the ridge. Bands appeared whose magnetization was flipped. The pattern continued, alternating like the bars of a code, stretching away from the ridge on both sides. Each stripe represented lava that had erupted, cooled, and frozen in the field present at that time. As new crust formed at the ridge and spread outward, it carried with it the memory of whichever polarity the planet happened to have when it cooled. The result was a magnetic recording of both seafloor spreading and field reversals, written over millions of years, and stored beneath the ocean all along. On land, the evidence is more fragmentary, but just as telling. Lava flows that erupted at different times, one on top of another, can preserve a stack of magnetic directions. In one layer, the minerals point roughly toward the present geographic north. In another, they point the opposite way. In others, they point somewhere in between, capturing the field in transition. Sedimentary rocks can also remember. As tiny grains settle through water, Small magnetic particles within them tend to align with the prevailing field. When the sediment is compressed and turned to stone, some of that alignment remains. It is a fuzzier record, blurred by slow motion and post-burial changes, but still readable with care. Taken together, these clues allow scientists to build what is called a polarity timescale, a map of when the field has been in its current orientation and when it has been reversed, extending back through tens of millions of years, and in some places even farther. Wide intervals where the polarity stayed the same for a long time, narrower ones where reversals were more frequent. No repeating rhythm, no simple cycle. When you look at a figure of that timescale, with dark and light bands stacked from the recent past down into deep geological history, it is tempting to treat it as data and little else. A useful tool for dating rocks, a background constraint for models of the core, a pattern to be explained. But there is another way to see it. Every band on that diagram corresponds to a span of real time during which the sky existed. The oceans moved, and living things struggled and adapted. Each reversal boundary represents a long interval when the magnetic field was changing in ways that no human eye ever saw. No witness was there to be surprised, or anxious, or fascinated. The only witnesses were stones, quietly cooling, and sediments, slowly settling. Those stones did not intend to remember. Memory, in this context, is just the long persistence of physical orientation under later conditions. But the effect is eerily similar to what we mean by memory in ourselves. Something transient happens. A pattern is imprinted in a medium, later, much later. That pattern can be read and interpreted by a mind that was not there at the time. When you pick up a rock used in paleomagnetic studies, the sample itself is small, a cylinder drilled from a lava flow or a slab cut from an outcrop. It might fit in one hand. Its color is ordinary, gray, rusted brown, dull, black. Nothing about it announces that. Locked within its minerals is a record of the direction of an invisible field at the time when early mammals were still tiny, nocturnal creatures, or when no complex life had yet reached land. The instruments that read these records are precise. They rotate the rock in controlled fields, measure the response, separate out different components of magnetization acquired at different times and under different conditions. The work is detailed and technical, but the premise rests on something simple, that stones can carry a memory far longer than any brain can. There is a quiet dislocation in realizing that the most reliable historian of Earth's magnetic past is not a written archive, not a digital database, but the crust itself. Human records reach back a few thousand years with any continuity. Oral traditions hint at older events, but they blur and fold as they pass from generation to generation. Rocks do not tell stories in words, but they outlast every library you could build. In a way that makes the polarity timescale a biography of the core written in a language that did not know we would one day learn to read it. You can step back even further. The idea that matter remembers is not limited to magnetism. Tree rings remember droughts and wet years. Ice cores remember ancient air. Coral skeletons remember past sea temperatures. But magnetized rocks are unusual because what they remember is not a local surface condition. They remember a planetary field. Each reversal captured in stone is a marker of an event rooted deep below, in the convecting metal ocean around the inner core. When you see alternating bands of normal and reversed polarity in an oceanic crust profile, you are looking at the shadow of that hidden dynamo, flickering over eons. The irregular spacing of those bands is a reminder that the dynamo has its own rhythms. Sometimes it holds a given polarity for several million years. Sometimes it flips, then flips again not so long after. The core is restless, but not in a way that yields to our craving for neat cycles. For a species that likes to predict, to forecast, to extend a trend line into the future. That irregularity is uncomfortable. You can say that. Statistically, reversals have happened many times. You can say that one will happen again. But you cannot mark a date on a calendar. The rocks offer a record, not a schedule. There is another, more personal layer to this, your own memory. The one you use to navigate your life is short compared to stone. It fades quickly. It can be distorted. It is influenced by what you want to believe about yourself and the world. When you think about your past, you do not see a clean polarity timescale. You see fragments, stories, highlights, gaps. Stones do not choose which events to record. They respond to physical conditions and then keep that response until they are destroyed. In that sense, they are more honest historians than we are. But they are also indifferent. They do not grieve the reversals they record. They do not care whether a long, stable interval ends. We stand between these two kinds of memory. On one side, the soft, selective storehouse of human recollection. On the other, the hard, impersonal record etched into the crust. Part of the work of understanding the planet is learning to read the second to correct the first. When paleomagnetists assemble a sequence of lava flows, align their samples, plot the directions, and see a smooth progression from one orientation through intermediate states to the opposite, they are watching a past reversal unfold in compressed form. What may have taken thousands of years in reality appears as a handful of points on a graph. The slow evolution of the field becomes, in human time, a single intellectual moment. In that moment, the illusion that certain features of the world are beyond change is quietly weakened. You realize that the direction a compass points is not timeless, that north and south can swap, that the protective field can wax and wane. And you realize that the planet has done all of this before, without witnesses who understood, without narratives to frame it. The stones understood nothing. They remembered anyway. It raises a subtle question. If a world can change so deeply, and remember that change in a way that no living creature notices until much later, what else is happening now, under your feet or above your head, that will only be fully legible long after you are gone? The basalt cooling tonight at a mid-ocean ridge, the sediments drifting down through the deep ocean, the lava quietly hardening in some remote volcanic field, are already writing chapters of a history that will outlast us. Somewhere in those new stones, the current state of the field is being fixed. Future minds, perhaps very different from ours, may one day read them and see our era as one thin band in a long series of flips and pauses. For them, our present north and south will be just one entry among many. For us, they still feel like part of the structure of reality. That mismatch between how things feel inside a moment and how they look from far outside it is not unique to magnetism. It is woven through every scale, from the history of a field to the history of a life. Seen from a great distance, a reversal is a clean line on a chart. Seen from inside, if you could somehow live there, it would feel less like a switch and more like a long unraveling. For a very long time, the dynamo, deep within the outer core, holds to a dominant pattern. Spiral columns of molten iron rise and sink, twisted by rotation, braided by magnetic feedback. Together, they sustain a strong dipole field, the large-scale north-south structure that we rely on without thinking. But that pattern is not the only one the system can support. It is just the one that currently wins. In the language of physics, many unstable configurations lurk nearby in the space of possible flows and fields. They are normally suppressed. The strong, coherent dipole dampens small perturbations, the way a clear rhythm in music can absorb slight mistakes without losing its beat. But as conditions change, that dominance can fade. The changes are slow. Heat leaks from the core into the overlying mantle at rates that, on human timescales, are essentially constant. On geological timescales, they vary. The inner core grows as more iron crystallizes at the center, releasing latent heat and light elements, changing the patterns of buoyancy that drive convection. The rotation of the planet itself drifts over immense spans. None of these processes has a single obvious trigger moment. They are more like background trends, nudging the system through a landscape of possibilities. At some point, the balance that has kept the dipole strong begins to shift. You would not notice it at the surface at first. Compasses would still point roughly north. The field intensity might start to decline, but by amounts small enough to hide inside ordinary variability. Inside the outer core, though, something else would be happening. The long spiral columns that once carried most of the magnetic burden begin to fragment. Smaller eddies, once kept in check, gain strength. Patches of flow that favor different magnetic orientations grow in size. Places where the local field points in directions that oppose the global dipole start to expand. Numerical simulations of the geodynamo, run on powerful computers, offer a glimpse of how this might look. In those models, as parameters are tuned toward reversal conditions, the once simple dipole weakens and a more tangled, multipolar field emerges. Temporary poles appear at odd latitudes. Regions of opposite polarity coexist, pushing and pulling on one another. You can think of this as a kind of internal argument. The core is no longer united behind a single large-scale orientation. Different convective structures generate different magnetic domains, and for a time no single pattern can fully dominate. The field at the surface becomes more complex, with patches where the direction deviates sharply from the old norm. From far above, if you could see magnetic field lines rendered as glowing threads around the planet, the picture during such an interval would be strange. Instead of a neat bundle of lines leaving near one geographic pole and entering near the other, you would see loops that connect at mid-latitudes, clusters of lines diving into the planet in unexpected places. Old pathways fading, new ones forming. It is in this intermediate phase that the field's strength can fall to a fraction of its usual average. Not everywhere at once, and not permanently, but enough to thin the magnetic shield that normally deflects charged particles. The sky near the equator might grow more restless with auroral lights. Radiation belts could swell, then shrink, then swell again. In everyday life, these changes would likely register first as technical problems. Satellites would fail more often. High-frequency radio communication could become patchier. Airline routes over polar regions might need to be adjusted more frequently to avoid bursts of radiation. Engineers would see the fingerprints of a shifting field in their error logs and design margins long before most people noticed anything unusual in the sky. Deep below, the cause would not be a single catastrophe, but a loss of coherence. The dynamo is a self-organizing system. Its large-scale order rests on constant feedback between flow and field. When that feedback is disrupted, the field can falter. One way to picture this is to imagine a crowd of dancers moving in a circle. As long as most of them keep roughly to the same rhythm and direction, the overall motion is clear. Now imagine small groups within the crowd starting to spin in their own circles, at their own tempos. At first, the main rotation might still dominate. But if enough of these local patterns grow, the original circle breaks down. The crowd becomes a patchwork of conflicting motions. For a while, there is no single direction that counts as the dance. Inside the core, the dancers are parcels of molten metal. The music is set by temperature gradients, rotation, and magnetic forces. During a reversal, the choreography breaks and reassembles, not in a moment, but over many lifetimes. From the perspective of a human life, that slow collapse of the old pattern and the emergence of a new one might sound almost gentle. No alarm bell rings to mark the beginning, No obvious border separates the last day of the old orientation from the first day of the new. Even if you knew exactly what to measure, the transition would blur into everyday noise. And yet, something fundamental would be happening. A direction that underpinned navigation, animal migration, and planetary shielding would be losing its meaning and then acquiring a new one. All while the beings living on the surface kept raising children, building tools, and telling stories that assumed a stable background. There is a kind of mirror here. In personal life, collapse before change often looks chaotic from the inside and inevitable from the outside. A belief system fails. Old habits stop working. The stories you tell about yourself no longer line up with what you actually do. To someone who only sees the before and after, it may look like a clean turning point. To you, it feels like confusion, contradiction, and a loss of orientation. The core goes through its own versions of that, without caring. It does not suffer its transitions. It simply passes through states where no single magnetic identity dominates. On the way from one long orientation to another, scientists who model these processes talk about instabilities, about symmetries broken and restored, about thresholds crossed when certain modes of flow become energetically favored. Beneath the technical language is a simple theme. Even systems that look remarkably steady day to day can carry within them the seeds of thorough rearrangement. During the build-up to a full reversal, the dipole moment of the field declines. Higher-order components, which describe more localized features, grow in relative importance. The geographic distribution of magnetic intensity changes. Some regions on the surface may experience much weaker protection than others. Temporary poles can appear and then vanish. The field lines in those areas can loop out into space and back in ways that differ significantly from the old pattern. If you lived in such a time, and if your society had the tools to map the field globally, you might watch atlases age more quickly than usual. Lines of equal magnetic inclination and intensity would drift and buckle. The printed diagrams that once felt timeless would need updates not every few human generations, but more often. You would see, in compressed form, what the rocks record over far longer intervals. The dynamo letting go of one arrangement and groping toward another. It is tempting to ask what precise trigger tips the system over. Which fluctuation? Which thermal anomaly at the base of the mantle? Which variation in inner core growth pattern marks the point of no return? But in complex systems, the idea of one decisive cause is often a projection. Many influences accumulate. At some stage, the old configuration simply loses its grip on reality. For us, the important fact is not which subtle shift in core dynamics comes first. It is that reversals do not arrive as external shocks. They rise from the ordinary behavior of the system itself. That has a quiet consequence for how we think about risk. There is no outside agency that decides to flip the field. No collision with another world. No passing star. The ingredients of change are built into the very process that keeps the field alive in the first place. The same convective motions that sustain the dipole also, over time, undermine it. The collapse before the flip, then, is not a failure of the dynamo. It is one of its natural modes. From far in the future, a researcher reading rock records of our era might see only that, at some point, the bands of one polarity gave way to bands of the opposite kind. They might infer, from subtle details in the stones, that the transition involved a drop in field strength, a rise in complexity, a period with multiple poles. They might even model the process, reproducing on a computer the restless flows that made it happen. They would not know what it felt like to live inside that slow collapse. Whether anyone noticed, whether any civilization saw the patterns in time and adjusted gracefully, or ignored them, or misread them as omens, we, standing in our own present, do not get to see the full arc of such events either. We only glimpse hints, long-term monitoring of the field, anomalies in certain regions, measurements that suggest weakening trends. It is too easy to swing between two impulses, alarm and dismissal, as if the only choices were panic or indifference. The deeper lesson is quieter. The core is a reminder that the foundations of our world can be both dependable and provisional at the same time. Dependable on the scale of a life, provisional on the scale of the planet. Between those scales, meaning has to find its place. You cannot wait for the core to settle into a final arrangement before you decide how to live. The dynamo will never do you that favor. It will keep moving, keep collapsing, and rebuilding patterns of magnetism, while on the thin surface above, generations rise and fall, each assuming in their own way that the invisible structures holding their sky in place are solid enough to lean on. At least for now, when the foundations of a world are provisional, the question quietly shifts from, are we safe, to what does it mean to live meaningfully inside something that never stops changing? Imagine standing at a high latitude under a dark, moonless sky. Today, the aurora is mostly a polar phenomenon. Curtains of light hang near the geomagnetic poles, green and red and violet shapes moving slowly across the night. They are the visible trace of invisible particles, guided by magnetic field lines, colliding with atoms in the upper atmosphere. Now imagine that the field has weakened, not vanished, just thinned. The protective bubble, the magnetosphere, still wraps the planet, but it is smaller, more ragged, less able to turn charged particles aside. In that world, auroras shift. They drift away from their traditional homes. The luminous ovals around the poles widen, sliding toward mid-latitudes, places that, for all of human history, rarely saw such lights begin to experience them more often. For many people, that would look like a gift. A spectacle once reserved for remote regions now appears above cities, farther from the poles. Night skies become more theatrical. Tourism flourishes for a while. Camera sensors fill with delicate arcs and ripples. But the aurora is a symptom. Each shimmering curtain is a sign that more energetic particles are entering the upper atmosphere. The same processes that paint the sky also ionize air, alter chemistry, and feed currents that can disturb power systems on the ground. The thinning shield would not transform the planet into an uninhabitable world. The atmosphere itself still absorbs most high-energy radiation. Ozone still blocks most of the dangerous ultraviolet from the sun. The surface is not suddenly stripped bare. Life has persisted through past episodes when the field was weaker, and it would almost certainly persist again. Yet risk would creep upward. High-altitude flight crews and frequent flyers, already exposed to more cosmic radiation than people on the ground, might face a measurable increase in dose. Astronauts in low Earth orbit, already vulnerable when passing through naturally weak regions of the field, would find those passages more frequent, more intense. Some orbits that are tolerable now might become impractical without much heavier shielding. Biology can adapt. To a point. DNA repair mechanisms already deal with damage from everyday background radiation. Evolution has unfolded under a sky that was never perfectly safe. If the field declined over many generations, small changes in cancer rates, mutation rates, and selective pressures might shape populations in ways that no single individual could feel directly. Civilization feels such changes differently. It has built delicate layers of technology that assume a certain level of natural protection. Satellites are a clear example. They move through belts of trapped radiation shaped by the magnetic field. Engineers design them with that environment in mind, choosing components, shielding, and orbits that keep failure rates acceptable. As the field weakens and its structure becomes more complex, those belts can swell and distort. regions of intense radiation can dip closer to Earth, brush more orbits, or linger over new geographic areas. Electronics that once lasted for many years might fail sooner. Instruments that once worked reliably might need to be switched off more often as they pass through hazardous zones. From the ground, this would register as a financial and logistical problem. Satellites lost earlier than planned, communication blackouts that occur slightly more often, or in patterns that do not match past experience. Navigation systems that require more frequent calibration. It would not feel like a single disaster. It would feel like a slow increase in friction. Power grids, too, would face more stress. During strong solar storms, charged particles driven into the upper atmosphere induce electric currents in long conductors on the ground. Transmission lines act as antennas. Transformers, designed for smooth loads, can be pushed towards saturation, overheated, or damaged. A weaker magnetic field does not guarantee more storms, but it can allow the effects of a given storm to reach more deeply into the system. In such a world, utilities would learn to live with uncertainty. They might build more redundancy into their networks, design transformers that tolerate more extreme currents, coordinate with space weather forecasts in a way that feels as routine as checking the meteorological weather today. The risk would be managed, not eliminated. None of this needs to be apocalyptic to matter. A planet does not have to turn hostile for life on its surface to become more precarious. A small increase in radiation, a modest rise in satellite failure rates, a few extra blackouts during geomagnetic disturbances can force a civilization to confront how much of its apparent stability rests on assumptions about an invisible field. And underneath the technical adaptations, there is something more intimate. We are used to thinking of danger as something that comes from outside. An asteroid on a crossing orbit, a nearby star flaring unexpectedly, a hostile act by other humans. Those threats have clear edges. They feel like events. A weakening magnetic field is different. It is not an intrusion. It is a change in the background conditions of existence, driven by the same core processes that have been running since the planet formed. No one chose it. No one can negotiate it away. It simply unfolds. Living under a thinning shield would mean making peace with that kind of change, with the idea that some shifts in the environment are not failures of planning or policy, but expressions of the planet's own long rhythms. There is a parallel in individual life. Some changes come from decisions, from choices you can trace back. Others arise from deeper processes you never controlled. The slow alterations of age, the way a body develops or fails, the way underlying temperament colors experience. You can respond, adapt, shape the consequences. But you cannot rewrite the basic fact that you are made of matter that follows its own rules. In the same way, a civilization facing a weaker field would find itself forced to distinguish between what can be fixed and what can only be accommodated. You can harden satellites. You can build better radiation monitors. You can reroute flights, reinforce grids, write new standards. You cannot ask the core to stop changing. On longer timescales, the biosphere itself might feel the effects in subtle ways. Increased ionization in the upper atmosphere can alter chemistry, potentially affecting ozone levels and the transmission of certain wavelengths of light. Patterns of cloud formation could shift in ways that are still a topic of research and debate. Climate is influenced by many factors, and any magnetic contribution would be braided into a complex web. The important point is not to exaggerate or minimize. A weaker field would not erase life. It would not sterilize the surface, but it would add another layer of variability to an already intricate system. And that variability would arrive on a schedule set by molten iron, not by human preference. It is easy, in the face of such ideas, to slip into grand language about fragility or fate. But the reality, like the physics, is quieter. Life has already passed through many episodes of stronger and weaker shielding. It has done so without reflective awareness. No animal in some previous reversal noticed the correlation between odd lights in the sky and subtle shifts in mutation patterns. We are the first species, as far as we know, to be able to connect those dots, to measure the field, trace its changes, model the flows that sustain it, and foresee some of the consequences of its future behavior. That capacity does not give us control, but it does give us a particular kind of responsibility. We can choose not to look, to treat space weather as a niche concern, magnetism as an abstract topic, reversals as curiosities, or we can choose to see ourselves as living within a nested set of systems, some of which move on timescales far beyond our own. In that view, planning for a weakening field is not about fear. It is about aligning our expectations with the world as it actually is. There is another layer still. Under a thinner shield, the night sky would be more restless, more alive with signs of the interaction between Earth and its star. It would be a visible reminder that the space around our planet is not empty. Charged particles spiral along field lines, slam into atoms, trigger cascades of light. In a stronger field, much of this theater is confined to places most people never see. In a weaker one, the theater travels somewhere. A person might stand under an unfamiliar aurora and feel both awe and unease, not because the lights themselves are dangerous at that moment, but because they gesture toward a deeper truth, that the conditions making this world habitable are dynamic, contingent, and not entirely under our management. You could respond to that feeling by retreating into smaller concerns, focusing on what can be controlled within the span of a human life. You could also let it loosen your attachment to the idea that safety must mean permanence. Perhaps meaning does not require an unchanging stage. Perhaps it only requires enough continuity for awareness to arise and act. Even briefly, the field will strengthen again. Someday, after a reversal completes or a long oscillation ends, the shield will thicken, then thin, then thicken again. As the core continues its slow work, each phase will leave traces in stone and ice. Most organisms will ride those changes without comprehension. A few, for some stretch of time, will understand what is happening and adjust their civilization accordingly. If we are among them, then living under a weakened magnetic field is not just a technical challenge. It is an invitation to see our place differently, not as rulers of a stable platform, but as latecomers on a world whose deep machinery moves at its own pace, offering a temporary shelter in which conscious life can appear. Look up at the sky and realize that the shield above it is both fragile and, for the moment, enough. There was at least one moment in Earth's recent past when that fragile shield was pushed hard, not over an age of stone slowly cooling, but within a span that brushes against the edges of human memory. Long before the first cities, while ice still lay heavy over vast northern lands, Earth's magnetic field slipped into a strange state. Scientists call it an excursion, a kind of aborted reversal. The name that has settled on this particular episode comes from a small village in central France, near old lava flows that carry the signature of what happened. La Champs, a quiet place on the surface, a marker of deep disturbance within. During this excursion, the field did not merely wobble, it weakened dramatically. In some reconstructions, the strength of the main orderly dipole drops to only a small fraction of its usual value for a comparatively short time, before recovering with its original orientation. The planet did not commit to a full flip. It tried on a different configuration, faltered, and returned. From the point of view of the core, this was just another rearrangement. Convection patterns shifted. Multipolar structures briefly took over. The dipole lost its grip, then slowly reasserted itself. No drama, no audience. From the point of view of the surface, If you could have watched it unfold from orbit with modern instruments, it would have looked like a surge of magnetic complexity. The neat north-south structure would have faded. Patches of reversed polarity would have grown here and there. Regions of weakened shielding would have opened and closed. The auroral ovals would have stretched, warped, and wandered far from their usual homes. The atmosphere would have felt this change. With less magnetic protection, more charged particles from the sun and from beyond the solar system would have reached the upper air. Ionization rates would have risen. Chemical reactions in the high atmosphere would have shifted, perhaps thinning the ozone layer for a time and letting more ultraviolet sunlight reach the surface below. Trees were there to notice, in their own way. As radiation levels in the upper atmosphere changed, the production of certain isotopes increased. Carbon in the air, drawn into leaves and wood, recorded the disturbance. Much later, humans would cut into ancient trees and ice, measure those isotopes, and see the spike. Another kind of memory, quiet and precise. The living creatures under that sky did not have models of the magnetosphere. They had bodies and instincts. Some may have seen more frequent strange lights at night, especially at latitudes where the aurora is rare today. The extra ultraviolet may have altered patterns of sunburn, of eye damage, of stress on plants and plankton. Over many generations, slightly higher mutation rates may have nudged evolution in directions it would not otherwise have taken. There are hypotheses that link this excursion to events in the biosphere and in climate. Some researchers have suggested that a thinner shield and a changed atmosphere could have stressed large mammals, contributed to extinctions, or tilted environmental conditions in ways that shaped which hominin species survived. Others urge caution, pointing out that many factors were at work: shifting ice sheets, changing oceans, complex ecosystems. The timing is suggestive, not conclusive. What is clear is that the Lachamp excursion was both short and intense on geological scales. The field weakened far more than usual, then recovered. The planet did not stay in that state long enough to settle into a stable, reversed configuration. It felt more like a spasm than a full transformation. If you think about reversals as slow, drawn-out episodes of global reorganization, excursions like Lachamp's sit in a different category. They are abrupt detours. The dynamo tumbles toward a new pattern, but pulls back before the change is complete. The rock record shows that such detours are not rare. They punctuate the longer bands of stable polarity, reminders that the path between steady states is not always smooth. For us, it is often the short, sharp disruptions that haunt the imagination more than the long background shifts. We can tolerate the idea of a slow drift, a gradual weakening over many lifetimes. It is the possibility of a sudden spike of chaos, even if it still plays out over centuries, that unsettles. The Lachamp event sits at the crossroads of those fears. It was brief, by the standards of the core, but long by human standards. An excursion that might have been felt, had there been a civilization with radios and satellites to feel it. A thinning of the shield that may have reshaped skies and climates, just enough to leave traces in pollen records and bones. In thinking about such an episode, another tension appears. On the one hand, there is the desire to see it as pivotal, a moment when the planet almost lost its protection, when life came under unusual stress, when evolutionary or cultural paths shifted. It is tempting to assign it a starring role in the story of our species, to imagine that some delicate chain of events, beginning under that unstable sky, led eventually to the humans who now study it. On the other hand, there is scientific restraint, the recognition that the evidence, while rich, is not decisive. Correlation is not causation. The Lachamp's excursion may have added strain to systems already under pressure. It may also have been just one more perturbation in a world that is always juggling many. We live inside similar tensions whenever we try to assign meaning to the events that disrupt our own lives. Sometimes we point to a particular crisis and say, "Here, this was the turning point." Other times, we admit that no single episode can carry that much weight, that what we remember as decisive was only one factor among many slow, overlapping currents. The planet does not resolve this for us. It simply presents a record, an unusual weakening of the field, a period of atmospheric change, hints of ecological response. How much of our story we choose to hang on that hook is partly a scientific question and partly a human one. What is striking, either way, is that this episode belongs to a time not impossibly distant from us. The people who lived under that sky were not abstract early life forms. They were humans and close relatives, already capable of tool use, of fire, of art. Some of the oldest known examples of human creativity date from around that broad era. Cave walls bear images of animals and hands from those centuries. In some sense, consciousness, as we recognize it, was already responding to a world where the magnetic field was doing something unusual. There is no sign that those artists knew anything about geomagnetism. The lights in the sky, if they saw them, may have been folded into myth or ritual, or simply accepted as one more aspect of a dangerous, beautiful world. Yet from our vantage point, it is hard not to let the two images overlap, a weakening shield above and small groups of humans below, marking stone with pigment, extending their presence just a little beyond the span of their bodies. It is a reminder that deep time is not only about distances beyond empathy. Sometimes, the phenomena we study are close enough that we can imagine the faces that looked up when they happened. Short-term chaos, whether in a magnetic field or a personal life, exposes how much we depend on expectations about the near future. The fear is not only of harm, but of disorientation, of losing the ability to project yourself even a little way ahead with any confidence. The Lechamp's excursion shows that Earth can, at times, deliver that kind of disorientation in its physical systems, not as punishment or lesson, but as a natural consequence of the way its interior works. It also shows that life can move through such episodes and continue. The field recovered, the sky quieted, the rocks kept their memories. The descendants of those who walked under that unstable auroral glow eventually learned to read those memories and give the event a name. From our present, with our own worries about sudden disruptions, there is a strange steadiness in that. Worlds can wobble, shields can thin, patterns can briefly collapse, and yet the long arc of time keeps flowing. Meaning, if it exists, does not depend on an unbroken calm. It may have as much to do with how beings like us live and think inside these temporary storms as with the storms themselves. Some storms never quite end, they just harden into features of the landscape. Small reminders that the calm you rely on was never completely smooth. If you could see the magnetic field around Earth from space, not as invisible lines on a physics diagram, but as a faint, shifting glow, you might expect it to look symmetric, a kind of soft, even shell around the planet, slightly squashed by the solar wind on one side and trailing a long tail on the other, but otherwise tidy. It is not tidy. There is a place, mostly over the South Atlantic Ocean and parts of South America and Southern Africa, where the inner edge of the radiation belts dips unusually close to the surface. In this region, the magnetic field at satellite altitudes is weaker than you would predict from a simple casus, centered dipole. The shield there is thinner. The armor has a dent. We call this dent the South Atlantic Anomaly. At the altitudes where many satellites fly, this anomaly is not a subtle nuance. Instruments see higher fluxes of energetic particles. Detectors meant to measure faint signals are flooded with noise. Electronic components accumulate damage more quickly. Operators plan around it. Spacecraft that pass through this region, often switch certain systems into a safer mode. The Hubble Space Telescope, for example, typically suspends its observations while crossing the anomaly, to avoid recording streaks of false light from high-energy particles masquerading as stars and galaxies. Astronauts on the International Space Station have reported seeing brief flashes when they close their eyes in the dark as they pass through, caused by particles slicing through their retinas. On the ground, nothing dramatic happens when the anomaly drifts overhead. People go about their days in Brazil or Namibia without any sense that, far above them, Earth's magnetic shield is slightly frayed. The atmosphere still protects the surface effectively. Radiation levels at sea level do not suddenly spike. The crack is high and technical, not a hole in the sky. From the point of view of physics, the anomaly arises because Earth's magnetic field is not produced by a perfect, symmetrical dynamo. The main dipole is tilted relative to the planet's rotation axis and offset from the center. Additional, more complex components of the field, generated by details of the flow in the core and by variations in the mantle above, distort the pattern. In the South Atlantic region, these distortions combine to reduce the field strength more than elsewhere. You could think of it as a place where the underlying restlessness of the core becomes visible in a focused way. The same messy, multipolar tendencies that drive reversals and excursions show up here as a localized weakness. The anomaly has changed shape and intensity over the years that we have mapped it. It drifts slowly as the internal field evolves. For scientists, it is a natural laboratory, a patch of space where conditions that might become more widespread under a much weaker global field already exist in concentrated form. By watching how satellites behave when they pass through, how instruments degrade, how particles move, we learn how a thinning shield affects technology and maybe, indirectly, life. For the engineers who design missions, the anomaly is something like a permanent storm on the route map. You cannot pretend it is not there, so you route sensitivity around it. You choose orbits that minimize time inside it. You make trade-offs between cost, performance, and resilience. That quiet dent in the field becomes part of the practical definition of what is possible. There is a quieter layer beneath the laboratory and the logistics. From the surface, from the standpoint of an ordinary day, the South Atlantic Anomaly is invisible. It is a feature of the world that you can only know through instruments and data sets. Yet it is real enough to alter how we look outward, to shape the images we take of distant galaxies, to change how long a satellite survives, to leave its mark on the plans of people who will never see it directly. Our lives are full of similar invisible dents, patterns of risk or vulnerability that you only discover when you start looking at the right scale with the right tools. A weakness in an ecosystem that does not show up until a particular species vanishes. A fragility in an economic system that does not appear until a specific kind of shock arrives. A habit of thought in a person that only reveals itself when a certain pressure is applied. On the surface, things look ordinary. Underneath, conditions are not uniform. There are anomalies. The South Atlantic Anomaly also complicates our picture of what a magnetic field is supposed to look like. It resists the comforting simplification that Earth has a strong, smooth field that simply weakens gently with distance. Instead, it reminds us that the field is a living pattern, full of quirks, shaped by deep processes and long histories. When you zoom far out, the planet still seems to have a single north and a single south, a reliable dipole. When you zoom in, you find regions where that neat structure fails, where the lines buckle and sag. The crack does not invalidate the overall shield, but it shows that the shield has texture. This tension between the big picture and the fine structure is familiar. You can say that a life is, in broad terms, stable and fortunate. From far away, the story looks smooth. Inside, there are anomalies, griefs, Fears. Moments when something protective thins unexpectedly. Those local weaknesses change the experience of the whole. Even if the outline of the life looks intact, standing at the edge of an ocean in the anomaly's footprint, you might feel nothing of this. The waves sound the same. The air tastes of salt. The stars rise and set. The crack in the armor is not for human senses. It exists in a space you will never visit, at altitudes where metal shells circle the world, carrying cameras and clocks and dreams of contact. And yet, decisions made in response to that crack cascade downward. They help determine which data we gather, which routes our machines take, how long certain experiments last. They shape what we know about the universe. Quietly, the way a warped lens decides which light reaches a sensor, the anomaly may grow, split, or fade in coming centuries. Its evolution is tied to the same inner workings that govern the long-term strength of the whole field. Watching it is one of the ways we monitor the state of the dynamo we cannot touch. It is a reminder that change in the deep interior does not only announce itself through grand, planet-wide reversals spaced over millions of years. Sometimes it reaches us as a localized inconvenience that hints at something larger. A crack, not yet a break. If you carry that image forward, it becomes hard to see the planet as a static, completed object. It feels more like an ongoing experiment, in which the rules are stable enough to allow life, but flexible enough to keep rearranging details in ways that no species fully anticipates. We live, then, not only under a shield, but under its imperfections. In the gaps and asymmetries of a field born in molten iron, we glimpse both our vulnerability and our capacity to notice. That noticing is, in its own way, a kind of armor too. Even if it cannot stop the core from moving, if magnetism is one way for a planet to betray its inner life, gravity is another, quieter one. Written not in light or color, but in the way motion refuses to follow a perfect line. From far away, Jupiter looks like surface, bands of cloud, swirling storms, an immense disk of gas reflecting sunlight. Everything your eyes and cameras can see happens in a layer that, compared to the whole, is skin deep. The true bulk of the planet is hidden. There are no windows into the deep metallic hydrogen, no direct images of whatever counts as its core. For a long time, that opacity felt like a wall. You could weigh the planet from the pull it exerts on its moons. But the details of how mass is arranged inside stayed mostly in the realm of educated guess. Juno changed the balance between guessing and listening. The spacecraft does not dive into Jupiter. It circles in a long, stretched-out polar orbit, dropping close over the clouds and then swinging far away again. Each close pass skims just above the top of the atmosphere, fast and low, like a stone grazing deep water before arcing upward. Along that path, Jupiter's gravity tugs on Juno, pulling a little more here, a little less there, depending on subtle variations in how mass is distributed beneath the clouds. Those variations are tiny compared to the planet's overall pull. Passing over a slightly denser region or a slightly lighter one might change the spacecraft's speed by an amount smaller than 1,000th of a millimeter per second. Yet Juno talks to Earth the entire time, sending and receiving radio tones whose frequencies we can measure with extreme care. The Deep Space Network listens for those tones and records how they shift. Each small change in frequency is a record of how Jupiter's gravity has nudged the spacecraft along its path. Radio waves make this possible in a way no other messenger can. A signal leaves a dish on Earth at a well-known frequency. Juno receives it, locks onto it, and sends it back at another precisely related frequency on a higher radio band. On the way out and back, motion and gravity alter the tone. If Juno is moving toward Earth along the line of sight, the signal comes back slightly higher in frequency. If it is moving away, the tone returns lower. This is the Doppler effect. the same principle that makes a passing siren rise and fall in pitch, applied to a spacecraft and a planet instead of a car and a listener. By comparing the transmitted and received tones, scientists reconstruct Juno's velocity along the line of sight with astonishing precision. Out of that changing tone, they reconstruct a gravity field. If Jupiter were a perfectly uniform sphere, rotating gently, the calculation would be simple. The gravitational pull at a given distance would depend only on total mass. But Jupiter is flattened by its rapid spin, bulging at the equator. Its interior is stratified, with denser material toward the center and lighter hydrogen and helium above. Deep winds may carry mass sideways in wide bands. All of this leaves fingerprints on the gravity field, small departures from the simple case. To describe those departures, researchers use numbers called gravitational harmonics. The leading one, often labeled J2, describes how strongly the planet's shape and mass distribution depart from perfect spherical symmetry in a way aligned with its rotation. Higher-order terms, such as J4 and J6, capture finer details of how mass is arranged with depth and latitude. Before Juno, earlier flyby and orbiter missions had given rough estimates of these harmonics. Juno's dedicated gravity experiment, using dual-frequency radio links and careful tracking during each close pass, sharpened those estimates dramatically. When researchers fit interior models of Jupiter to those harmonics, they can rule out some possibilities and favor others. A compact, sharply defined core produces a different pattern from a diffuse, fuzzy region where heavier elements blend gradually into metallic hydrogen. Deep, fast winds that extend thousands of kilometers below the visible clouds add another kind of signature, creating an asymmetric component in the gravity field that Juno can sense. Comparing simulations to the actual Doppler data lets scientists estimate how far those winds reach into the interior and how mass must be layered to match the measured field. None of this is seen directly. There is no camera at the center of Jupiter sending back images of a blurred core. There is only a pattern in the way a small, human-made object speeds up and slows down as it falls past a giant world, and a set of equations that connect that pattern to invisible structure. There is something quietly humbling in that. To learn about the interior of a planet, we do not crack it open. We watch how it moves other things. Even the tides Juno measures are indirect. The large moons, especially the volcanic world Io, raise bulges in Jupiter's deep fluid layers as they orbit. Those bulges shift the gravity field just slightly. Juno feels those shifts as additional variations in its motion. From them, scientists estimate how easily the planet deforms under tidal forces, which in turn constrains how dense and rigid different layers must be. If you step back, this way of knowing starts to feel familiar. We rarely see the deepest parts of another person's life. Most of what we know comes from small deviations in their motion. A pause before they answer. A change of subject. A plan quietly abandoned. We infer inner landscapes from these external tugs and hesitations. The core of another person is never directly visible. It is reconstructed, always imperfectly, from the way they move through shared space. Juno's gravity experiment is a planetary scale version of that kind of inference. Stripped of psychology and left with pure dynamics, the spacecraft does not care why Jupiter is the way it is. It simply follows the path set by gravity. The interpretation that turns Doppler shifts into density profiles is our work, layered on top. There are limits to what the data can reveal. Different interior configurations can produce very similar gravity fields. A slightly heavier core balanced by slightly lighter outer layers may be hard to distinguish from the reverse. Deep winds and gradual composition changes can trade places in the models, no matter how precise the tracking. The step from gravity back to interior is never entirely unique. That uncertainty is not a flaw to be erased. It is a reminder that we are far away, working with the few messengers the universe allows across large distances. For Jupiter, gravity, magnetism, and light are those messengers. For the Milky Way as a whole, ancient variable stars will serve a similar role, carrying information about times and places we can never visit. Juno's long series of close passes, spread over more than a decade, has turned the planet's pull into a kind of time series, a record of how one world tugs on another. Each passage adds detail to the map, refines the harmonics, and narrows the range of plausible interiors. No single orbit reveals everything. Knowledge accumulates as a sum of small corrections, each one carved out of a tiny change in a radio tone. Seen this way, the mission is not just about Jupiter. It is about the method itself, listening for minute shifts in motion, and trusting that, if we are patient, they will say something true about what we cannot see. That is, in the end, how we approach much of the universe. We look for slender traces, measure them, and allow ourselves to be led from the surfaces we can image toward interiors we can only infer, constrained by data and shaped by time. When the first gravity maps were turned into possible interiors, the picture that came back from Jupiter did not look like a tidy cross-section of layers. It looked like a sign that the way we had been imagining giant planets was, in a quiet but important way, wrong. For a long time, the standard story about Jupiter was simple enough to sketch. Deep in the center, a compact core of rock and ice. Above it, an envelope of metallic hydrogen, dense and conducting. Above that, a lighter molecular hydrogen layer, topped with the cloud decks our cameras can see. The core, in this picture, was like the seed crystal in a growing planet, sharp-edged, solid, the thing that started it all. When Juno's gravity measurements were folded into interior models, that sharp seed blurred. To match the detailed spectrum of gravitational harmonics that Juno had returned, scientists found they had to give up the idea of a small, well-defined core. Instead, the best-fitting models showed an extended region deep inside Jupiter where heavy elements are mixed gradually into the hydrogen and helium, spread outward across a large fraction of the radius rather than confined to a compact ball. In other words, the core was there, but not where we expected it to be, and not in the form we wanted. It was fuzzy. In these models, the inner regions of Jupiter are enriched in heavy elements compared to the outer envelope. But rather than piling all that material into a small central lump, the enrichment extends outward, perhaps across nearly half the planet's radius or more, creating a diluted core whose boundaries are blurred. Hydrogen remains the most abundant component by number, even in the deep interior, and may even dominate by mass, with heavier elements dissolved throughout. This was not what classical formation theories had led many people to expect. In the textbook sequence, a giant planet like Jupiter begins with a solid core that assembles from rock and ice in the protoplanetary disk. Once that embryo is large enough, it pulls in gas rapidly and builds a massive envelope. Most of the heavy elements arrive early, before runaway gas accretion. Later, the envelope is mostly hydrogen and helium. The result should be a fairly sharp compositional step. Dense core here, lighter envelope there. Juno's fuzzy core did not fit comfortably inside that picture. It suggested either that the original compact core had somehow been eroded and mixed into the envelope over time, or that the process of formation and accretion was more complex than the simple two-stage story implied. One early attempt to explain the dilution proposed a dramatic event, a giant impact. In that scenario, a large planetary embryo, perhaps carrying a mass of heavy elements comparable to much of Jupiter's original core, collided with the young gas giant in a mostly head-on crash. The impact shattered and stirred the central regions, mixing rock and ice into the surrounding metallic hydrogen and leaving behind a diffuse, extended core that could persist for billions of years. It is an arresting image, a world already immense, struck by another, and carrying the scar not on its surface, but in the arrangement of its interior. For a time, that vision fit well with the gravity data. Simulations showed that such a collision could, in principle, create the kind of diluted structure that Juno's measurements seemed to demand. More recent work has complicated that story. High-resolution simulations of impacts and mixing suggest that, under many plausible conditions, heavy material stirred up by a collision tends to settle again relatively quickly. We're forming a more compact core instead of staying diluted across a large region. Other models of formation show that composition gradients might arise more gradually, as the growing planet pulls in both solids and gas over extended periods, or as the core itself erodes through slow interaction with metallic hydrogen. A newer line of research leans toward a quieter explanation. Jupiter's fuzzy core may have formed naturally as the planet grew, with heavy and light elements becoming intermingled in the deep interior, rather than through a single catastrophic event. In this view, the diffuse core is not a scar but a consequence of long, complex evolution in a convective, partially stratified fluid interior. Whichever route turns out to be more accurate, the central fact remains: Jupiter does not have the neat, layered structure that many models once assumed. Its core is extended, compositionally smeared, structurally ambiguous. It is striking how much that bothers us. There is no law of physics that requires a gas giant to have a sharp-edged core. The equations allow all sorts of gradients and mixed regions. The fuzziness is a problem mostly for our desire for simple categories. Core versus envelope, rock versus gas, center versus surroundings. When you picture the inside of a world, it is comforting to imagine clear boundaries. A core you could, in principle, outline with a single continuous line, an inner realm that is definitively this, not that. The idea that, instead, there might be a long, murky transition zone where no single label fully applies feels less tidy. It resists the urge to summarize. We do something similar with ourselves. We talk about the core of a person as if there were, somewhere under habits and roles, a compact, unchanging center that explains who they are. Then experience intrudes. People change with time, with pressure, with chance encounters. Traits that seemed central soften. New patterns emerge. The more closely you look, the harder it becomes to draw a sharp inner circle and say, here, this is the real self. All else is surface. Jupiter's fuzzy core is a planetary-scale reminder that not every center is simple. The surprise did not stop with Jupiter. Analyses of Saturn's gravity and the way that planet vibrates, studied through its rings and through the subtle behavior of its field, point to a similarly diffuse, extended core region there as well. The idea that giant planets commonly have diluted cores has moved from anomaly to serious, if still debated, possibility. That shift ripples outward into our thinking about exoplanets. If the largest worlds in our own system do not match the clean core envelope stereotype, it is risky to assume that distant gas giants do. Formation models have to make room for composition gradients, for mixing, for histories that leave behind ambiguous interiors. At a deeper level, the fuzzy core breaks a quiet habit. The habit of treating deviations from our preferred pictures as temporary oddities that will, with enough data, be smoothed away. Here, more and better data only sharpened the oddity. The more precisely Juno measured the gravity harmonics, the more firmly the models pointed toward a diluted core. The anomaly did not retreat under scrutiny, it crystallized. There is a kind of maturity in accepting that. In science, as in life, some puzzles are resolved by finding that the world really does match the simple story. Once you account for noise, Others are resolved by admitting that the simple story was never true, only convenient. Juno forced planetary scientists to rewrite parts of their mental script about how gas giants grow and what they look like inside. That rewriting is still in progress. New equations of state for hydrogen and helium at extreme pressures. New simulations of convection and double diffusive layering. New ideas about how heavy elements move in metallic interiors. All feed into the ongoing attempt to reconcile gravity data, formation theory, and physical plausibility. From outside that technical work, the broader pattern is easy to recognize. We begin with firm outlines. Here is what a planet is. Here is what a core is. Here is how they must be arranged. Then a new kind of observation arrives, and those outlines soften. The object we thought we understood turns out to be stranger, more gradated, less obedient to our categories. It can feel, in those moments, as if understanding has slipped backwards. The neat mental picture dissolves, replaced by a more complicated, less decisive one. But the movement is actually forward. The universe is refusing to match the cartoon, and we are adjusting. Jupiter, with its fuzzy core, sits now as a kind of warning against overconfident simplicity. The largest planet in our system, visible as a bright point to every casual skywatcher, turns out to contain an interior that challenges not only specific models, but the way we expect structures to behave. As the story of this planet's center continues to unfold, another story is preparing to enter, a story about stars whose own structures and pulsations can be used to read not only their interiors, but the ancient architecture of the galaxy itself. There, too, our intuitions about clear edges and clean centers will be tested, and the answers will arrive through indirect traces, carried not by spacecraft, but by the steady, rhythmic changes in the light of very old suns. Before we let Jupiter recede into the dark, there is something else it keeps insisting on showing us, that even when you think you have reached the core of a thing, there is still another unsolved layer wrapped around it. Jupiter's magnetic field is not just strong, it is strange. From Earth, you mostly meet it indirectly, through the auroras near the poles of that distant world. Unlike Earth's dancing lights, which fade and flare with solar storms, Jupiter's polar glows are almost permanent. They are fed not only by the solar wind, but by material from its volcanic moon Io, funneled along magnetic field lines into the polar atmosphere. The result is a ring of near-constant energy, a storm of particles and light that hardly ever turns off. Beneath that display lies a dynamo very different from Earth's. Instead of a thin, molten shell of iron, Jupiter has a vast region where hydrogen is squeezed so hard that it behaves like a metal, with electrons moving freely. In that deep layer, convection and rapid rotation work together to generate a magnetic field. On paper, you might expect something not unlike an enlarged version of Earth's dipole, a strong bar magnet, tilted a bit, but broadly symmetric. Juno's measurements of that field have made it clear that this expectation is wrong. When scientists mapped Jupiter's magnetism using Juno's close passes, they found a field that is lopsided and oddly concentrated. One hemisphere carries an outsized share of the magnetic complexity. There are regions near the equator where the field lines dive inward in a way that would be unthinkable for a simple bar magnet. One of these regions has been nicknamed the Great Blue Spot, a patch of intense, locally inward field set in a sea of different orientations. Seen projected onto the planet, the pattern looks almost like an unfinished drawing. Strong, focused structures cluster on one side. The other side is quieter, more dipole-like. The symmetry that simple dynamo models tend to produce has been broken. Explaining that pattern is hard. Some of the oddity may come from the fuzzy core. If heavy elements are diluted outward through a large region, rather than confined to a small center, They can create gradients in density and composition that affect how fluid moves and where convection is strongest. Some layers may become partly stable against overturning, forcing circulation into preferred channels. Those channels, in turn, can shape the dynamo in ways that leave their mark on the field. Rapid rotation adds another constraint. It tends to align flows along the spin axis, carving the interior into columns. But if some of those columns pass through regions where the fluid is less free to move, or more heavily loaded with heavy elements, they may behave differently from their neighbors. The field that emerges is the sum of all these influences, braided and competing. We are still at the stage where models chase observations. Different teams build different versions of Jupiter's interior, tweak conductivity, adjust composition gradients, and see whether the resulting dynamos produce something as asymmetric as the actual field. Some succeed in reproducing certain features, like the equatorial inward patch or the polar structure. None yet feels definitively right. In that gap between data and theory, it is tempting to reach for a narrative of progress, the idea that given enough time, enough computing power, enough equations, we will end up with a clean, satisfying explanation. A story in which the strange magnetism becomes inevitable. The only possible outcome of the deep conditions. Maybe we will. But Jupiter's field also suggests another possibility, that some systems are so sensitive to their interior history that no single neat story will ever quite capture them. Slight differences in how the planet formed, in how heat escapes, in how composition is layered, may lead to different magnetic personalities, all compatible with the same broad constraints. From a distance, you can say that Jupiter has a powerful, roughly dipolar field, generated by convection in metallic hydrogen. That statement is true, and for many purposes, enough. Up close, you see the great blue spot, the hemispheric imbalance, the skewed complexity. Those details matter if you are trying to understand how dynamos work in general, or how deep winds slice through conducting layers. Something similar happens every time we try to describe a person. You can say that someone is kind, or cautious, or restless, and capture something real. But the closer you get, the more you notice the unevenness, the ways that kindness shows up in some situations and not in others, the pockets of impatience, the unresolved contradictions. The magnetic field of a life is not perfectly aligned. It has its anomalies and quiet regions, its permanent storms and unexpectedly calm zones. Jupiter offers us an image of that complexity written in plasma and field lines. There is also the matter of time. Juno has not just mapped the field once, it has watched it change over the course of its mission, measuring small shifts in the magnetic pattern from one close pass to the next. Those shifts suggest that features like the great blue spot are moving, being stretched by deep flows, perhaps drifting in longitude. The field is not only asymmetric in space, it is evolving in time. We stand, as usual, in the awkward position of having a thin slice of that evolution, a handful of years of detailed data, compared to the long lifetimes of convective structures in a giant planet. We do not know whether the strange configuration we see now is a long-lived arrangement or a transient phase in a much slower dance. This is a pattern that repeats through all of cosmic science. We arrive late, look around quickly, and try to infer the full story from one frame of a film that has been running since long before we existed. It is to our credit that we can reconstruct as much as we do from that frame. It is also a source of permanent uncertainty. Jupiter's magnetism, then, stands as an unfinished answer in more than one way. It is unfinished because our models are still catching up with what Juno has revealed. It is unfinished because the planet itself is still rearranging its interior and its field, in slow motion. And it is unfinished because our questions keep changing. What began as a simple curiosity about how strong the field is has unfolded into deeper questions about how cores form, how elements mix, how rotation, stratification, and convection conspire to generate patterns we did not anticipate. There is a temptation, in the face of any unfinished answer, to rush past it, to declare a provisional explanation good enough, file the mystery away, and move on. Another temptation pulls the other way, to insist that until the explanation is complete, no understanding is possible at all. The reality is quieter. We live in the space between those temptations. What we know is partial but real. What we do not know is vast, but not featureless. In the glow of Jupiter's permanent auroras, powered by a field that ought to be simple and is not, you can see a kind of preview of the way stars and galaxies will look when you peer closely enough. Clean diagrams give way to uneven, history-laden structures. The neat symmetry of theory bends under the weight of actual events. And yet, even in that mess, patterns emerge that are stable enough to trust. Ships of plasma follow field lines. Radiation belts hold to certain shapes. The planet's giant magnetosphere carves out a cavity in the solar wind that other objects pass through and feel. In our own lives, we do something similar. Inside a character that is never fully settled, we still manage to act as if certain traits, certain commitments, are solid enough to build on. We navigate with partial maps, and most of the time, they serve. Jupiter's strange magnetism does not resolve that tension. It simply reflects it back to us, on a scale too large to hold in the mind at once. A world with a fuzzy core and an uneven field, holding its storms in place while everything inside keeps moving. Soon, we will leave it behind and turn to stars that flicker in rhythmic pulses instead of roaring with bands and spots. There, the questions of interior structure and long memory will return in a different form, written not in gravity and magnetism, but in light that brightens and dims with a precision that, somehow, survived from the early universe to now. Before we listen to stars that beat in time like distant hearts, it is worth pausing with a simpler rhythm, the slow, forgotten journey of the light that already touches your skin. Think of a morning you remember clearly. You step outside. Light falls on your face. Shadows sharpen and soften. Everything in that moment feels immediate. It feels new. The warmth on your cheeks seems to belong to that exact instant. It does not. The energy arriving as sunlight began its trip inwardly old by the time it reached you. To follow it back, you have to go down, past the glowing surface of the sun that we can see, into a place that no human eye has ever looked upon directly. At the very center, the sun is not a ball of fire. It is a dense, crushing plasma. Temperatures climb to many millions of degrees. Pressure is so high that protons, which normally repel each other, are pushed close enough for quantum tunneling to let some of them fuse. In that fusion, mass is converted into energy. The bookkeeping is strict. A tiny loss of mass corresponds to a release of energy that, scaled up by the number of reactions, becomes the luminosity of a star. Each successful fusion reaction throws out energy in various forms, including high-energy photons. These are born not as gentle, visible light, but as fierce gamma rays, in empty space. A gamma ray would cross astronomical distances almost unimpeded. Inside the sun, it barely makes it a short distance before it is scattered, absorbed, and re-emitted by the sea of particles around it. The core is thick with matter, the mean free path of a photon there. The typical distance it can travel before hitting something is tiny compared to the radius of the star. What might have been a straight flight becomes a random walk, step after step, collision after collision, direction forgotten each time. If you tried to follow a single quantum of light from its birth in a fusion reaction to its emergence at the surface, you would quickly lose any sense of a path. The photon is scattered, its energy handed to an electron, then reissued as one or more new photons at different energies, which then scatter again. The identity of the original gamma ray dissolves into a cascade. What remains is the flow of energy outward. On average, that outward diffusion takes an astonishing time. Many estimates suggest that a parcel of radiant energy can wander inside the sun for hundreds of thousands of years before finally reaching layers transparent enough to let visible light escape freely into space. The ray that brightens a leaf, that sharpens the edge of a building, that reflects from your hand, has almost certainly been part of that slow migration. It began its outward journey long before any human stood under a sunrise. Long before any mammal existed to squint at the morning. There is something quietly disorienting about that. You live in a stream of light that remembers conditions deep in the star from ages you would call prehistory. And yet you experience it as something that happens right now, as if it were freshly minted for your day. Further out from the core, the character of the sun changes. There is a wide radiative zone where energy continues to move, mainly by radiation, by this slow, repeated scattering. Above that, the plasma becomes unstable to convection. Hotter material rises. Cooler material sinks, forming churning cells that carry energy more quickly. In that layer, the random walk of radiation gives way to the rolling motion of matter itself. Near the visible surface, the photosphere, the gas finally becomes transparent enough that photons can travel almost unimpeded. A photon released there can cross the gap to Earth in a few minutes. That last leg is fast, nearly straight. Simple to describe, it is the part we teach first. The deep interior, with its long delays and tangled paths, hides in the background. If you stand in sunlight and close your eyes, you do not feel the time embedded in it. You do not sense the many scatterings, the fused nuclei, the compressive weight of layers above. Your body registers warmth. Your brain supplies associations. Morning, beginning, clarity. The star above you is not beginning anything. It is continuing a process that has been running for billions of years, in which hydrogen is slowly turned into helium and energy leaks out from the center in a steady, almost indifferent way. The fact that, for a brief interval, some of that energy falls on a planet where eyes and thoughts have evolved is not what the process is about. It is an outcome, not a goal. Still, knowing the history does something to the feeling of the moment. The light on your face is no longer just a local event in the atmosphere. It is the final act of a journey that began long before your entire species appeared. That does not make your experience less real. It simply stretches the timeline behind it. We like to imagine ourselves at the start of things. Morning as a fresh page. A new year as a reset. A technological breakthrough as the beginning of a new era. The photon's path through the sun is a quiet correction. By the time you encounter many events in your life, they are carrying the accumulated history of processes that began far earlier and far deeper than you can see. Even on the scale of personal change, the pattern holds. A realization that feels sudden has usually been building for a long time. Thoughts have been scattered through conversations, books, stray comments, unnoticed feelings, all bumping into one another below the threshold of awareness. Then, something small pushes the system past a point where the energy can move more freely, and an idea rises to the surface with the clarity of sunlight. It feels new. It is also old. The sun does not care how we read it. It fuses at its own pace, balances gravity with pressure, sheds mass and light into space. But for us, this star is both a physical object and a clock. Its stable output sets the conditions for climate. Its slow brightening over deep time defines a window during which complex life can thrive on Earth. Its eventual changes will close that window. Inside that long arc, the journey of a photon is one of the smallest stories you can tell and one of the most revealing, It shows how something that seems immediate can actually be the last step in a chain of events far too long to hold in mind at once. It shows how a moment can be both present and ancient. When the photon finally leaves the sun, it has forgotten everything. It moves in a straight line, a packet of energy without memory. The only record of its long struggle outward is encoded in its energy and in the statistics of the light field as a whole. Yet when it arrives here and triggers a reaction in a leaf, or a signal in the cells of your retina, or a tiny rise in the temperature of your skin, it participates in a very different kind of memory, the kind that nervous systems and ecosystems build. Plants use sunlight to drive photosynthesis, storing energy in chemical bonds. Animals eat the plants or one another, building bodies and behaviors out of that stored sunlight. Brains, which are just specialized arrangements of those bodies, use the energy to make and maintain patterns of connection. In those patterns, something like a self appears, capable of remembering not just physical conditions, but experiences. The energy that wandered through the sun for so long ends up drawing outlines of people, forests, oceans, cities. It powers the screens that show images of stars and galaxies. It feeds the instruments that measure the sun itself. There is a strange loop in that. The star emits energy. Some of it, after a long delay, helps build organisms that can think about stars. Those organisms then aim instruments back at the star to reconstruct the process that produced the energy. Consciousness, in this narrow sense, becomes one of the ways the sun's output is spent. You can push that thought in different directions. One is to feel a kind of intimacy with the star, as if you are made of its attention. Another is simply to notice how indirect the path is from cause to consequence. Nothing in the nuclear reactions in the core of the sun is aimed at awareness. Awareness rides on them anyway, soon. We will look at stars that do something even more unlikely. They brighten and dim rhythmically, with a precision that has turned them into tools for measuring the shape and age of the galaxy itself. Before we step into that deeper darkness, it is enough to stand, for a moment, in daylight, knowing that the light around you began its escape long before any human knew there was such a thing as a journey to trace. The light that reaches you from the sun is old, but the light from some other stars is not just old. It carries the rhythm of something that has been beating steadily since long before your planet cooled. Imagine a star that cannot hold still. It swells and shrinks in a regular cycle. Its surface brightens and dims, not chaotically, but with a period you could, in principle, set a clock by. For a short time it is larger, cooler, and more luminous. Then it contracts, heats, and its brightness falls, only to rise again. Lyrae stars live in that rhythm. They are small compared to many famous variable stars, roughly half the mass of the sun, give or take. And they sit in a particular phase of stellar evolution called the horizontal branch. They have already burned hydrogen in their cores, grown into red giants, shed part of their outer layers, and settled into a stage where helium fusion is steady in the center while hydrogen burns in a shell around it. In that state, some find themselves in a narrow band on the diagram astronomers use to plot stars by temperature and brightness. That band is called the instability strip. In it, small changes in the star's structure are not damped out. They are amplified. The outer layers become like a resonant shell, expanding and contracting in a repeating pattern. The mechanism that drives those pulsations is rooted in the behavior of partially ionized helium in the stellar envelope. In certain layers, when the gas is compressed, it becomes more opaque and traps heat instead of letting it escape. The trapped energy increases pressure, pushing the layer outward. As it expands, it cools and becomes more transparent, letting radiation leak out, losing pressure, and falling inward again. The result is a self-regulating cycle. a star-sized version of a heartbeat that works without intention. Each Lyrae star has its own period, typically less than a single Earth day, often only some fraction of a day. That rhythm repeats many hundreds or thousands of times over the course of a year. Over the lifetime of such a star, the pulses number in the millions. To an individual watching the light curve, those cycles can feel like a precise instrument ticking. To the universe, they are the ongoing tremors of an old, stable object that has found a way to shed energy in a regular pattern. They are old in another sense. The classical Lyrae population belongs to what astronomers call population 2. Metal-poor stars formed when the universe was younger, and heavy elements were scarce. Their typical ages are on the order of 10 billion years or more. They are contemporaries of the early Milky Way, relics of an epoch when galaxies were still building up their structure from merging fragments and in falling gas. Recent work has found that not all Lyrae stars fit that single story. Some, likely formed through binary evolution in the disk, are younger and richer in heavy elements. But the dominant image that emerges, especially in globular clusters and the halo, is still of an ancient population, stars that have been shining and pulsing for most of the age of the galaxy itself, because their intrinsic brightness is relatively well understood once you know their pulsation properties. Lyrae stars serve as standard candles. Measure how bright one appears from Earth. Compare that to how bright it should actually be, given its period and color. The difference tells you how far away it is. Do that for many such stars, and you start to sketch not just where a few points of light sit, but the three-dimensional skeleton of the Milky Way. In the halo, Lyrae stars trace out a vast, diffuse sphere and elongated streams, remnants of smaller galaxies that fell in and were torn apart. In the bulge, near the crowded center of the galaxy, infrared surveys like VISTA and VVV have revealed Lyrae stars hidden by dust and outshone by younger, brighter populations. They form a more spheroidal, centrally concentrated distribution than the bar and X-shaped pattern traced by other, younger stars. That difference suggests that the bulge's oldest heart may have been built from mergers of primordial clusters, leaving Lyrae as surviving witnesses. If you look at maps built from these stars, the sense of a neat, flat disk with a bright center gives way to something more layered. A thin disk of gas and young stars, a thicker disk, a central bar, above and around it all, a halo of ancient Lyrae, some belonging to the galaxy's original population, others tracing the paths of past collisions and accretions. The galaxy, seen through these variables, is not one thing. It is a sum of histories. On human scales, we often speak of a center as if it were a single place that everything else orbits, physically or metaphorically. The center of a city, the center of power, the center of a life. The Milky Way seems to indulge that language. There is a central region, a bulge, orbiting stars, and at the very core, a supermassive black hole. Yet when you spread Lyrae stars across that image, the idea of a single meaningful center starts to weaken. These stars are not concentrated only at the very geometric center. They thread through globular clusters that orbit far out in the halo. They populate streams that loop above and below the disk, tracing paths of long-vanished companions. They sit in the inner halo and classic bulge region, but in a distribution that does not match the younger bar. The center that matters to them is not a point. It is an extended region of deep gravitational potential and long history, smeared out over many kiloparsecs and many billions of years. Even more destabilizing is the step outward, to cosmology. When people hear about the Big Bang, it is easy to imagine an explosion from a single location, with galaxies flung outward into pre-existing space. In that picture, the universe would have a center, somewhere in the past, or perhaps in a hidden region of space. The actual story is different. Space itself expanded. Every point moves away from every other, on large scales, because the distances between points grow, not because they are flying away from a central origin. There is no privileged point you can point to and say, "Here, this is where it all began." Everywhere else is outward. The universe has no center in the way a firework does. Our Lyrae stars participate in that centerless expansion no differently from the sun or from your own body. They simply formed early and have been stable long enough to serve as markers. We use them to measure distances inside the galaxy and in nearby systems. We use them to reconstruct the assembly of halos, to trace accreted structures, to estimate ages of stellar populations. Through them, we read the story of a galaxy that has no special place in an expanding cosmos, and yet is full of internal structure and memory. There is a shift, somewhere in that realization, that mirrors a shift many people go through in their own lives. As children, it is easy to feel as though you stand near the center of things. Your town, your family, your species, even your era, can feel like the reference frame that quietly organizes everything else. Over time, that sense erodes. You learn that your culture is one among many. Your planet is one among many. Your galaxy is one among many. And the universe itself offers no middle or edge that puts you in a privileged location. At first, that can feel like loss. The loss of a central place. The loss of a straightforward story. Our Lyrae stars offer a different way to see it. They are not in the center of the universe. They are not even always in the visible centers of galaxies. Yet they carry a disproportionate amount of information because they are old, because they are relatively simple to understand, because they pulsate with reliable rhythms. They become anchors for our maps of space and time. Their importance does not come from being located at a central point, but from being reliable witnesses, spread throughout the structure. Consciousness, in a universe with no geometric center, can play a similar role. It does not occupy a privileged location. It arises late, on small worlds, orbiting ordinary stars. It is temporary, bound to biological processes that will not last. And yet, while it is here, it can look around, connect patterns, reconstruct histories, and notice that certain ancient stars have been beating out their rhythms since long before there were eyes to see them. In that sense, our Lyrae stars are part of a kind of galactic memory. Their ages tell us that some structures in the Milky Way are almost as old as the galaxy itself. Their distribution shows where the earliest populations ended up after mergers and accretions. Their chemistry encodes how rich the gas was in heavy elements when they formed. They are like old individuals in a community who remember not only their own early life, but also what the place they live in used to be, before newer buildings and newer stories arrived. When you place yourself in that picture, you are not central, you are late. You live in a galaxy whose oldest surviving stars have seen most of its history. You stand on a planet that formed long after the first globular clusters, long after the initial collapse of the Milky Way's gas. The universe has been making and rearranging structures for billions of years without any reference to your arrival. Late is not the same as excluded. To live late in a story is to have access to more of it. You can see the traces of earlier chapters. You can use stars like R.R. Lyrae to read not just where you are, but how this place came to be. You can understand that the center you might long for does not exist, and still find orientation in the patterns that do. Somewhere in the halo, a very old R.R. Lyrae star is pulsating right now, brightening and dimming over a timescale short enough that, with the right telescope, you could watch a full cycle in a single long night. Its surface moves, its light curve traces a precise, repeating shape. Inside, Helium burns quietly in a core that has been stable longer than any mountain on Earth. You are not the center of its story. It is not the center of yours. But for a brief overlap in time, you can use its rhythm to place yourself inside a galaxy, inside a universe, that has been carrying on without a center for far longer than any map, or any myth, suggested.